Assigning oxidation numbers is very much like assigning charges to ionic compounds. Charges can be considered oxidation states. However, oxidation states also extend to covalent molecules based on how they share electrons and electronegativities. So the ionic ones are pretty straightforward. Let me zoom in on these here. CaF2, remember that's a subscript. They didn't pull into this program very well. This is an ionic substance, so their oxidation states are their charges, -1 and +2. And we see that the two fluorines balance out the calcium. For the next one, carbon and hydrogen. Well, we're not looking at charges here because carbon doesn't have a charge on the periodic table per se, but we do use hydrogen as a reference since it is going to keep its +1 charge the vast majority of the time, and then we can figure out what the oxidation state, we don't say charge, we say oxidation state, of the carbon is going to be. And this is just based on how they share electrons, because they don't share evenly. So if I have +6 with the hydrogen, each one of these carbons has to be -3 to balance it out. They look like charges, we call them oxidation states. H2O, actually either way you do this one, it works. Both of these have their charge is equal to their oxidation state in the vast majority of cases, so we can just use those as our reference points for each other, and water is pretty straightforward. With iodine and chlorine, now we have a problem of electronegativities. One of them can be standard to its charge, but the other one can't, because they can't both be -1. That won't balance out. Since chlorine is more electronegative, chlorine will retain its -1 oxidation state, which is similar to its charge. Iodine is less electronegative, which means the chlorine is going to be stealing them, or the chlorine is going to be stealing them from away from the iodine. That iodine is going to be +5. Okay, sounds strange, but it's covalent. They're oxidation states, not necessarily charges. KMnO4. We can look at this two different ways. Yes, this thing is ionic. Okay, there's a polyatomic ion there. So if you recognize the MnO4 ion, you know that that MnO4 ion is -1, then you know that potassium is +1. Okay, now that works for their charges, but we want every monoatomic atom to have an oxidation state, not just the MnO4 to be -1. I want to know what the manganese is and the oxygen. So we don't really want this -1 here. That -1 is actually pretty good to recognize that our potassium is +1, because that is a monoatomic ion by itself right here. But now we need to go into the MnO4 minus. So oxygen, we take its Q is going to be -2, which gives us a total of -8. And for the permanganate to balance with that potassium there, it needs to be +7. The other way to look at this, if we look at sulfate, SO4 2-, is to just look at the polyatomic ion. Let me rewrite this one here. It doesn't matter what the sulfate is attached to, you can pull it out. So if my oxygen itself has a -2 oxidation state, this is where we see my sulfur has to be +6 because I need a remainder of -2. That whole thing needs to have a charge. So I actually don't want these to balance out. I want them to equal a charge. Sulfur is going to be +6. I've got 2 extra electrons. And if we go back to the permanganate, we can do that as well. Even if we didn't look at the potassium and like, oh, let's recognize that this is polyatomic and write it separately. MnO4-. I'll say -1 so you can see it better. Same thing. Oxygen is -2. There are 4 of them, so -8. And if I need a 1 left over, I need this to be +7. So the trick here is with polyatomic ions, you do not need to look at the whole molecule. If you want to pull it out separately by itself, you can look at the oxidation states based on the polyatomic ion charges as well. And when we look at reactions, we see the usefulness of these oxidation states. If I just scan through these, do the easy ones first. The aluminum is by itself, and the iron is by itself on each side. So those are both going to be neutral, because there's no charge designated. Oxygen in these ionic compounds is going to be -2. Aluminum is always +3. And iron we'd have to calculate, but we can see here it's going to be +3 as well. And here's where we're going to go with this real soon. Since this is reactants and products, what we're tracking here is the changes. Look what the aluminum did. It went from 0 to 3. And the iron went from 3 to 0. Meanwhile, the oxygen did nothing. So we're gonna put some names with those things, but that's the reason we're gonna keep track of these oxidation states. Here's some just examples that we're really, for those numbers to change, those charges to change, we're talking about electron transfers, moving from one thing to another. Almost any energy producing organic process in your body does these things: combustion, metabolism, Krebs cycle, the electron transport chain. All of these things, we start to call them redox reactions, where the electrons are moving one thing from another, and we can keep track of them with these numbers. So here's a bunch of examples. Let's first assign oxidation numbers, and then let's see how they change and what is oxidized and what's reduced. So my oxidation numbers here, hydrogen and oxygen are both 0. On this side, hydrogen is +1, oxygen is -2. So we see that the oxygen went from 0 to 2, -2. That went down. We're going to call that reduction. My hydrogen went from 0 to 1. That oxidation state went up. That is an oxidation. Okay, so the hydrogen went through oxidation, the oxygen went through reduction. And the definitions of those: to be reduced, to go down from 0 to 2, we had to gain electrons, and for oxygen to go up, we had to lose electrons. So those same charges work like they normally do. Zinc over here is 0. The copper and the zinc ions are already labeled +2, so this copper on the other side is 0. This one's easy to keep track of. The copper is going from 2 to 0. That's going down, which is reduced. And the zinc is going from 0 to 2, which is up, and it's getting oxidized. All right. We go down a little bit more, and we see an ionic compound. Silver is +1, -1. Chlorine is -1. Hydrogen by itself is 0. This hydrogen is +1. It's already labeled. Silver is 0 all by itself. And these chlorines, they're already labeled, but they're -1. So we see what the changes are. And we see that silver is going from 1 to 0. That's being reduced. And oxygen, what's changing? Hydrogen is going from 0 to 1. The hydrogen is being oxidized. A little trickier here with this big one. There's a lot going on in here. My top row is the reactants, my bottom row is the products. MnO4. So the oxygens are each -2, and we did this one earlier. My permanganate is +7. Hydrogen is +1. Over here I have, let's rewrite that, oxalate. It's C2O4 2-. Okay, there's 5 of them. My oxygens are each going to be -2. To have a -2 left over, each one of those carbons has to be +3. So my carbon is +3, my oxygen is -2. My manganese is 2+ over here. My CO2, oxygens are -2 each, and there's 2 of them. So my carbon is +4. And then standard water, hydrogen is +1, oxygen is -2. So we look at all of that to find the changes, and we see that the the manganese is going down. That's being reduced. And we see that the carbon is going from 3 to 4. That's being oxidized. Now, we wouldn't say the carbon necessarily is oxidized and the permanganate is oxidized. We always talk about the reactants, but in this case, we have to talk about the whole molecule itself. Even though the oxygen's not the one losing the electrons, we say the permanganate. The whole thing is being reduced into manganese. And we would say oxalate. This whole oxalate molecule is being oxidized into carbon dioxide. That's the way we would say it. It's not really just the one element by itself. Some of these other examples we got away with it because a lot of the atoms were by themselves. We only talk about reactants, never the products. We say the reactants are oxidized or reduced into the products. So we only really identify the reactants. So up here we would say copper 2 is reduced, not copper, because copper's over here. Copper 2 is reduced into copper, and zinc is oxidized into zinc 2, the zinc ion. Okay, so just be careful how we say it, but we'll just track those things. So here's another example. We need to balance this reaction. Sometimes balancing these equations is exactly like it usually is. You just kind of trial and error, count your atoms on both sides. Sometimes, however, it's a little bit more complicated. The reason we know that this one is going to be normal is if I look at all of these molecules, they don't have any charges on them. This is just normal balanced molecules. Let's just normal balance the equation, okay? Let's do some trial and error here. I notice my hydrogens are not balanced, so let's get those both, let's go back to black. Okay, let's get those both to 6, and that will get me my 2 nitrogens, that'll give me 3 oxygens, 3 lead. So there we go. And if we look at oxidation states, we get this bonus question now. How many electrons are transferred? Well, we need to know some oxidation states. So let's go assign these. +2, -2. Here I've got a +1 hydrogens, -3 nitrogens. There should be an arrow here. I don't know where that went. Okay, there's the arrow. This nitrogen is neutral. Hydrogen +1, oxygen -2. Lead by itself is 0. So the charges going down are lead. So now we look at the actual numbers. Lead went from 2 to 0. There are 2 electrons being transferred there. But then we get a bonus question. How many leads are there? There are 3 of them that are losing those 2 electrons. All right? There are 3 of them. Or they're gaining electrons. I'm sorry, they're reduced. They're gaining electrons. That's going to give me 6 electrons there. So let's go to the other side. The nitrogen went from -3 to 0. That's the one that lost electrons. There's 3 electrons there that were lost. But how many nitrogens are there? There are 2 of them undergoing those 3 electrons. So there's 6 again. So the question here is how many electrons were being transferred? It's 6. It's not 12. We don't add these together. They're happening in concert with one another. So what we're saying is these 6 electrons that are lost in the oxidation, they come over here and they are gained by the reduction. They're the exact same electrons. They come off of one thing and onto another. Notice that that 6 is balanced. So they are lost from one, gained from the other. 6 electrons are being transferred. And that helps us explain why we get to a problem like this, and we say balance the equation. And, well, there's one of everything. It's balanced. Yes, but the charges are not balanced. And this was what makes redox a little bit more challenging than just a normal balanced equation. If we put all our numbers in here, 0, 2, 3, and 0, my aluminums are changing they're losing 3 electrons, but my coppers are only gaining 2 electrons. Those aren't balanced. We need those charges to balance as well. So a simple one like this just lets us look at these and say, hey, the common multiple is 6. So if my coppers, where am I here? 3 coppers will give me 6 electrons there. 2 aluminums will give me 6 electrons. Now I've got 6 electrons transferred on each side because I need those electrons balanced as well. Okay, so here's another one. We got 0, plus 1, 0, there's an arrow again missing somehow, and plus 2. So my silver is reduced from 0 to 1. There's 1 electron there. And my copper is oxidized from 0 to 2. 2 electrons there. Those electron transfers are not balanced. We need 2 more down here. So 2 silvers and 2 silvers will give me a balanced reaction. So here, again, let me put in the arrow where it needs to be. Here the arrow is right here. Okay. That is a pretty bad arrow. Let's look at all our oxidation numbers. And that water is a product. Maybe I can write it over here if I can squeeze it in. H2O. There we go. Okay. Get rid of that. Hydrogen is plus 1. The ones with ions, they're pretty straightforward. The tin over here is neutral. Oxygen is minus 2. It's a nitrate. It's NO3 minus 1. Okay, let's read this right. Subscripts aren't working well. NO3 minus 1. So my oxygen is minus 2, which makes my nitrogen plus 5. My chlorines are minus 1. This is Cl6 minus 2, so SnCl6 minus 2. And then that makes my tin plus 4. NO2, my oxygen is minus 2, nitrogen is plus 4, there's no charge on that one, and then my water is pretty standard, plus 1, minus 2. Okay, so let's find everything here. If you can find where everything's changing, you're not going to be able to balance this just by going back and forth inspection. You need to balance the charges as well. So if you start with the charges, my nitrogen is going from 5 to 4. If you start with this, everything else will fall into place. Nitrogen is going from 5 to 4. That is 1 electron. And that's being reduced. My tin is going from 0 to 4. That's 4 electrons being oxidized. Those numbers need to match. What I need to do is I need 4 times my top one, and that'll get me 4 of the bottoms. So this nitrate, I need 4 of those, and then I'll get 4 NO2s. That will balance the rest of the equation. That means you don't touch this tin, you don't touch this tin chloride ion, you don't touch the nitrate. Now we've got 4 of them, and we have 4 NO2s. Once you get these electrons to match, you can leave those species alone and just fill in the rest of the blanks. So let's see what else is going to fall into place here. I don't need the oxidation numbers anymore because the oxidation numbers were just there to help me. Oh, they're not going to erase, are they? We're just there to help me figure out what's oxidized and reduced. So let me get a new color for all the coefficients here. All right. So if I have 4 nitrogens on each side, my tin, I have 1 tin on each side, that'll suffice. 6 chlorines, we know that 6 chlorines is right, so let's come over here and make 6 chlorines. Not 6 tins, 6 chlorines. And then we look at, the only thing we have left is the hydrogen. So when we go over to the product side, we have, oh, nope, we got to worry about the oxygens too. I have 12 oxygens over here, because I know this 4 is correct, and I only have 8 over here. That means we need 4 more waters on this side. So let's put a 4 there. And that 4 is going to give me 8 hydrogens, so I need to come over here and have 8 hydrogens. So my coefficients, it's a little messy in there. It's 8 hydrogens plus 6 chlorines plus tin plus 4 nitrates makes SnCl6 minus 2, one of those, plus 4 NO2s plus 4 H2Os.